comparing to others, and it provides the reasonable the accuracy of the cluster I have used in my dissertation, the K-means algorithm. Actually, not K-means, it's an EN clustering algorithm, which is a model-based. We will see later. Okay. So another problem of the K-means is it starts at the local optimum. Local optimum. What does that mean? Local optimum.
Stuck.
It's not a correct optimal solution.
Not the
So, for example, so I like to cluster this, the time series data, this is a time, this is a value. So how many peaks over here?
2 weeks.
The 2 peaks. But we have the local peaks. So if your algorithm starts over here, it will determine this one as the peak cluster. That is the same problem. So sometimes because it try to audit, because the previous data we don't consider if the already passed. So based on that, decide the current location of the centroid. So if you go for the wrong direction, like the local optima, so you cannot get away from the local optima. So it always try to find this. Okay, that is the problem of the local optima. So weakness. This K-means used for n-dimensional space, the continuous data, or anyway. But we can apply actually the little change for the categorical data by assigning the value, whether we can use the mode. What is the mode? What is the mean? Average. What is the median? It's the middle value. You can, alright. What is the mode? Frequency. So we can use, instead of the distance, we can use frequency for closeness. How much closer? Or we can use that. There are variants, so there's the problem. So, but it can be the Medoid. Medoid, we will see the example of the Medoid. Instead of the imaginary centroid value, so mean value is not the actual data. The Medoid decide the closest data from the centroid as the new centroid. That is the Medoid. Okay. Problem is the K. And this one is the K-means algorithm, very sensitive to the extreme value, like this one. For example, I have this value. Okay. What is the centroid of this one? So if that is too extreme, okay, then I have another one is here. All of this data belongs to here because of the outlier. Okay, so it's not it's sensitive for such an extreme value or outlier data. You should be careful. Also, it's not suitable for the non-convex shape. That is the previous example, arbitrary shape, because it tries to form. Ideal case is circle or the ball star, volume stars. Okay, that is the K-means algorithm. There are a lot of the variation of the K-means algorithm, including the paper that is assigned for your second reading assignment, I think. Okay, and we can use the mode or the frequency and some dissimilarity measure or the similarity measure. So you can apply the different similarity measure, different the feature vector, and also different the objective function. Okay. So I'd like to finish today's lecture with the K-Medoid. K-Medoid use the real value, closest value from the centroid instead of the centroid. So for example here, this one is selected from we will determine one of these as a centroid, which is called this one, and something like that. Okay? That is a K-Medoids clustering algorithm. Okay, so next class we will continue the other clustering algorithm, include the hierarchical, then